Hello, welcome to lecture 10 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to extend the notion of the partition function to include systems in diffusive contact, and that will lead to the famous Gibbs sum. Okay, so in lecture 6, we considered a system A in thermal equilibrium with a reservoir, and we asked what was the probability that system A is in a specific state which we called beta. And we found that this probability is just the number of times state beta appears in the list of states of the total system, so this is the numerator, divided by the number of states of the total system. So this term is the number of times state beta appears in the list of states of the total system, because this is the number of states of the reservoir having the complementary energy. And recall that epsilon beta is the energy of state beta. So this is a very basic probabilistic formula. Just the number of times an event happens divided by the number of events, of possible events. And then we manipulated this equation using the entropy and reached the very important conclusion that this probability depends only on the energy of the state, the temperature of the reservoir, and the partition function. Now we're gonna again poke a hole between the two systems so as to put them in diffusive contact. So now we're going to assume both diffusive and thermal equilibrium, and we're going to ask again what is the probability that system A is in a specific state beta. And again, this probability is given by the number of times state beta appears in the list divided by the number of states in the list. And again, the number of times state beta appear in the list is the number of states of the reservoir that having the complementary energy, and now also the complementary number of particles. So M naught is the total number of particles, is the number of particles of the total system, and N beta is the number of particles in the state beta. And the reasoning we're going to follow is essentially the same we followed to find this equation for the partition function. We begin by getting rid of the number of states of the total system because we cannot calculate this, so we divide the probability of state beta appearing with a state alpha. So these two are any states of system A. So with this ratio, we get rid of the number of states. Then we use the definition of entropy, recalling that now entropy is a function of two variables because the multiplicity is a function of two variables. So with this definition, we can express the multiplicity in terms of the entropy, just like we've done in lecture 6. And we expand the entropy of the reservoir, keeping only the first order terms. So now because the entropy is a function of two variables, we have two first-order terms instead of only one. And now we use the definition of temperature to replace this term with the inverse of the temperature. So this term becomes this term. And we use the definition of potential. Recall that this is the total potential, to replace this term with this term. And now we use this expansion in the expressions for the entropy, so this term becomes this term, and likewise this term becomes this. Then we move this to the numerator, we get a minus sign, and then these two terms cancel each other. Okay, so these two terms will cancel, so they disappear. Then we can move this term back downstairs and group the energy and the number of particles of each state within the brackets. That's why we get the negative sign here. It has to be positive, so we have negative and negative. And we know that this ratio is valid for any pair of states, beta and alpha, which means that the absolute probability must be equal to the exponential divided by a normalizing function. So we can find this function of the temperature and potential by requiring that the sum of the probabilities over all states of system A is equal to 1. And if we do that, we find that this function is the sum of the exponential over all states of system A. And this function is called the Gibbs function. So this is only the extension of the partition function to a situation where system A is also in diffusive equilibrium with the reservoir. And we're going to use this expression when we discuss the Fermi-Dirac distribution. So that was all for today, very brief lecture. And next time we're gonna take a look at the states of an electron gas, and that's gonna lead to the Fermi-Dirac distribution that will be discussed after the next lecture. So see you there.